So derive an expression for the elastic compliance C, and C equals delta, right? Delta over P. In terms of the plate dimensions and the elastic, the modulus, the stress in equation 224 is a normal value. We just say normal value. Say, for example, this sigma equals P divided by 2BW. P is a load, and we have area and B and 2W. So this is only applies when A is much less than W. The expression derived is only approximate for finite widths. So I'll just give you some hints. So we have this the G is the energy release rate, and G equals and P squared and divided by 2B and DC and D2A. So this is the G. So you can see just this one can be arranged this way. Okay, P squared and 4B and DC and dA. And finally, we have the relationship between the energy release rate and this is the derivative of the C, and C is compliance with respect to this crack length. So this is energy release rate. For this kind of configurations. And then we use this, we also know that the G equals and G squared, is a sigma. And sigma squared and pi A and divided by the Young's modulus. Good. So what's the sigma? I said, and sigma equals P divided by 2WB. Sigma equals the load. We assume the load is uniformly distributed to BW. So you can just put this plug in, and you will have a P squared IA and 4B squared and W squared E Young's modulus. So this guy equals this. So this guy equals this. So you can just take the derivative. So this equals this. And you can, I'm sorry, not take the derivative. Integral. Integral the C equals to the integration over DC. You understand, guys? Can I stop here? Or you want me to go all the way down? I can stop here now, right? I'll give you more hints. So this guy equals this guy, right? I can write DC is a function of BA. Do you guys agree? Calculus. This equals this. I can write DC equals the function of something. You just rearrange them and multiply by DA. Do you guys agree? And then you do the integration on both sides. And then you can have C. Okay. So here is C. Because I love you guys so much. and I will give you some hints. B equals C equals pi and 2BE A over W square and plus a C constant. And then I just leave this one to you guys. Is it fair enough? You like this kind of vision? But I want you to go through this one, make sure you understand each of these steps. And you just don't give me this one, right? If you just give me this one without any intermediate steps, just give me this one, I'll give you big cross and 0.
Why is it only approximate for a finite width plate?
So this, because the side effect, we have side effect. What? The side effect. So this one to be straight, and the plate need to be infinitely high. Theoretically, okay? But usually when we do handle this is engineering applications, as long as this plate is big enough when compared with the crack length, and we still think this one holds. Good question. So this is our first problem. Second one, this material axis, this one resistance R is described in that equation, and A has this one, and crack length is this is 1 and this is a 2. I want you to handle this and 2 of them. So how to solve this kind of the problem? Is a 2.5. So 2.5, we know that it is okay. This one growth resistance R, we know R. When R has this one and crack length inches, the elastic modulus of this material consider wet plate with a through crack that is made for this material. You can see if this plate fracture this one, compute the following. If this plate has any crack length, this one, and compute the following. And so what I want to tell you guys is that, so under what condition, so instability, okay, MC instability. So instability is a very, very critical condition. And for this instability, and we want is the G equals R, right? So under release rate and equals the current resistance. So that is the first condition. And the second condition, we also want to know that the change of dG T with respect to A. So this one is equal condition, is a critical condition, is a dr of dA. Do we still remember these two conditions? Right? So these are critical conditions. If this equation changes to inequality, and then something will happen. You guys agree? So you can just use this one, right? So this is G equals R, and for this plate, and we have the G equals the pi sigma square and A C. Because when I C here, because it's critical, I assume if this condition is met, the crack initiates or the crack propagates. So that's the reason I denote this one as AC. Young's modulus, this E equals the R. Equals R, I use the 6.95 and A minus A naught and the power 0.5. Keep in mind, so here is the AC critical. So this AC and this A and they are the same. Alright? Because we want to know at this critical condition and the correct initials. So these two okay, this is our first condition. For second condition, you can take second condition, and you need to take the derivative. And G take the derivative of AC is equals and pi and sigma square Young's modulus, this guy equals something. What is a factor? And you need to calculate. So here, for this side, take the derivative of this R with respect to A. And I will give you, this is a factor you need to calculate. You need to calculate this factor. So here, I will have A minus A0, because you are taking the derivative 0.5, 0.5 minus 1, and minus 0.5. Right? So because I know that here is AC, and here is, so this one, you need to calculate this factor. I give this task to you guys. And then, after you get these two equations, and you can finish and these computations in the volume. And I will leave these to you guys. Alright? But first, this one equation is very, very essential. Second one, this is a factor, this is a constant. And you should know that based on this R, and how to do the derivative, right? Take the derivative. I don't know that is originally in 0.5, but out this guy subtracted by 1, you have minus 0.5. But here needs to be changed. This is original factor, but this one needs to be changed. I leave this task to you. Questions? So, guys, so this one, okay? So this equation is used for the standard unit. This is international unit. For this one is for the US customer unit. And you can just try this one or try this one, only one. If we want to do twice, I'm also okay. I will give you a bigger praise, bigger heart. You guys watch the TikTok? TikTok video, whenever you like this as a video, just put a heart there, right? I'm kidding, right? Questions regarding this? No question? No question? We are going to next problem. This next problem at 2.6. Let me take a photo, and then I can post this one on the cameras also. Some students are missing today. The 2.6 is very similar to the 2.5. The 2.6 it says, suppose that a double cantilever beam we have crack on edge, we have we find it this way. It's fabricated from the same material considering this one. Same material means that the R curve is the same, resistance curve. Calculate the load at failure and amount of stable crack length growth. The specimen, the dimensions are given as follows. So we use the same conditions, that are two equations, okay? So these are two equations, and then you can just solve the problem. So this is 2.6, let me write down, 2.6 is very similar to the 2.5. So 2.7. So use the same. We use the same. Calculate a nominal linear elastic material with a radian R and use the R we just used for 2.5, 2.6. I suppose that one test is performed on wet plate with a through crack, and the second test on the same material is performed on double cantilever beam. If both tests are conducted in load control, would the GC values at stability be the same? If not, which geometry will result in higher the GC and why? Okay, for this problem, for this 2.7, so the driving force curve we call it G. For the through crack is linear. Well, G varies with for this one, okay? So for this is through crack, the driving force equals pi sigma square A and divided by E. For through crack, it is linear. See, you can G and A, and they have linear relationships, right? However, for the DCB, is no. For the DCB, you can look at what I give you last time. For the DCB, the G equals for the DCB, and you can just check the DCB for DCB and G is proportional with A squared. I leave this one to you guys. For the DCB, I told you one equation. Get that equation, okay? Get that equation. Now, and still these two geometry would have different points of tangency on R curve. And even though we have the same R curve, I suppose, this R curve, but this one is for the through hole thickness, through hole. For this one is for DCB. So this is the same R, but they have one is so this is for the through hole. And for the DCB, it is a problem. Okay? It is a problem. Without loss of generality, I just draw a problem. I'm not good at drawing. But this guy, the problem. So this is for DCB. And you can see carefully, you can see very clearly that even the R is the same, but these two curves are different. And then you will know G equals R, DG, dA equals dr and dA. For these two different curves, and you will have different the critical A. You understand, guys? Okay, what I want you guys to tell me is that to draw this curve, I'm gonna make some comments about this. Right? If you can do this mathematically, that will be much better mathematically. For here, I want you to not just give me this one. I want you just to give me the exact equation that I told you. Questions? No question. Let's look at last one. So last one, beginning with equation 220. Derive expression for the potential energy. Let's see the 29. The 220. So 220 is this sigma f equals for the penny-shaped floor of crab on pi e gamma s 2 1 minus nu square multiplied by a, the whole thing would have 1/2. So this is for penny-shaped curve, for the penny-shaped floor. Potential energy, okay? For potential energy, we have this. For potential energy, we have potential energy with respect to A. A is a credit surface, minus is minus sign, and this equals B WS. WS is the work required to create the two surfaces, one crack for two surfaces. Divided by the derivative of the crack face. For the penny-shaped crack, or for the penny-shaped crack, right? For penny-shaped crack, for penny-shaped crack, we have this WS. Okay? WS is work needed to create two surfaces. And penny-shaped is a circle, right? It's a circle, two circles, top, bottom. So it equals pi a squared. This is area, right? Area multiplied by gamma s. And gamma s is a surface energy. And gamma s is a surface energy. So this is only one surface. I need to have two because on which crack, any crack, it will have two surfaces. And keep this in mind. So as a result, this is WS, then I can have dWs over dA. A is the area. It equals 2 gamma s. Yes. Okay. For this gamma s. Now, here I can, for this equation, for penny-shaped, the gamma s is related to sigma f. So you can write here, okay? Based on here, you can see right gamma s equals a function of this is and sigma f and a, sigma f and a. And then you just let this gamma s multiplied by 2 equals dWs. And then I would leave this one to you. And keep in mind, dA, right? dA equals let's see, A equals I A squared. You guys agree? dA equals 2 I A dA. I want to just give you this one because we are going to use this. You understand? So I will leave this one to you, okay? And I hope you guys finish everything by yourself, and you are welcome to talk to me whenever you have a problem. But I want you to finish this one independently. And the cooperative learning is also encouraging, but you need to understand by yourself. Copying and pasting, you will not learn anything, trust me. Okay, so this is our homework. And then we talk about our new thing. The new thing. Now first we talk about the relationship between the stress intensity factor and the energy release rate. And for through thickness crack, through thickness is the most commonly used one in infinitely wide plate subject to remote tensile stress. And we know that G is written this way, pi square sigma square A divided by E prime. So I put E prime here. Previously we used E. I have E prime here. What is the E prime? Okay, E prime is effective. This is Young's modulus. Because for the 2D problems we have the case scenarios. One is a plane stress, one is a plane strain, right? For plane stress, Young's modulus E equals the E prime. However, for plane strain, you need to do some manipulation to calculate the E prime. But these two equations, they are valid for both cases. Understand, guys? So you need to have this concept. E prime is the effective Young's modulus. It is dependent upon whether the problem you are solving is plane stress or plane strain. Okay? So keep this in mind. Now, I'm going to derive on how to validate and how to prove that G, the relationship between G and Ki. And when we see this relationship, we can write the relationship between G and I. But now I'm going to show you guys from the very beginning and to tell you how can we establish the relationship. So I give you a very, very detailed derivation. First, you need to know the G derives the global behavior, but the K is a local parameter. Also know that the Professor Irwin, you can see Professor Irwin appeared many times in this context. He's a very famous guy in the fraction mechanics. Professor Irwin conducted a crack closure analysis that provides a proof. So what does that mean? A closure, crack closure. So they want to do this, okay? So this is suppose, and so this is my original crack length, which equals A. So for this case, I have the stress distribution along this surface. That means theta equals 0. Okay? You understand? Orientation is just in front of the crack. So theta equals 0. I have this kind of sigma y, the distribution of sigma y, which is inversely proportional to the r square root. So this is my stress. Now suppose I have A plus dA. dA is very, very tiny. This dA is very, very tiny. Okay, I just imagine from here to here, I have a crack growth. And this growth is the delta A, which is very, very tiny. Alright? Now, I want to show you that. So, how much energy you need to apply to close this crack? To close, this is the crack growth increment, crack increment. How much energy you need to apply? So is this energy required is the same as energy the material needs to have so much crack growth? Yes, right? Yes, right, guys? It's just a different way. For here, from here and to here, suppose I needed the energy to be x energy to have so much crack growth. So this energy should be equal to the energy I require for you to close this guy from another direction. Okay? Suppose we have this already. I want you to apply energy and apply a certain amount of energy to close this part. You understand, guys? So Professor Irwin just seen this problem from the inverse direction. You understand? So this is energy, okay? Energy release rate equals delta U, delta A. Delta A is the crack growth, and delta U is the energy you need. So multiply by 1 over P. So for here, for simplicity, we just assume the P equals unity. This is unity, and it equals 1. So we just like this guy. This is the derivative of U with respect to A goes to 0, and then we can get G. Are you guys okay? Now, if you are guys okay, you can DU. What is energy? What is energy you need? Well, now sigma y. Suppose I have the dx here. So this is very, very small dx. And sigma y multiplied by dx equals what? Equals the force, right? Stress multiplied by, I have a B here. B is the another direction, the dimension. So B multiplied by dx equals the surface area. And surface area multiplied by sigma y is the stress. So the whole thing will be equal to the force, right? But I just deleted this B because B equals 1. You understand, guys? So actually, I should write dot capital B, but B equals 1. Because B is in this direction, the thickness. So the force multiplied by the displacement. You see the displacement from here to here. How much you need to move? And so you can close. So displacement. Force multiplied by the displacement. So this is multiplied by 1/2. Displacement force multiplied by half is the energy you require.
So the du on the left-hand side, that's energy, but then the uy is displacement,
Uy is the displacement.
and then the du is energy.
Yeah, this U is energy.
Okay.
This is Uy is the displacement in y direction. That's a good question. Understand? Okay. So Uy, and then we calculate Uy. How to calculate Uy? And Uy, you can just see here, okay? So I just treat this one as my new crack. And here, I can just theta equals pi. Theta equals pi. How much it is? And so you can just based on a table 2.2. And theta equals pi. we can use this equation to calculate. So here is R. R is a displacement from this R is the distance between the point of interest to the crack length. So this is the crack length. And so divided by 2 pi multiplied by kappa plus 1. And then here is something here. So this is a sigma. So this uy, this one multiplied by this. So this is uy. So for the crack A plus delta A, okay, for crack A plus delta A. So this one is from the equation from the table. And for the crack A plus delta A, uy needs to use to change this one a little bit. 2 mu kappa plus 1. Here, the Ki, but the Ki here is referring to this new condition, is a new crack. And A plus delta A, and then multiplied by the square root delta A minus x and 2 pi. So here is the 2 pi here. And 2 pi is a 2 pi delta A minus x. Delta A minus x is the distance from the crack tip to the point of interest. So this one is for a crack. That means one more time, guys. Right? So this one is for the crack. This is so this is the R, the distance, the R. Right? So because I want to support this is a pi. So this is minus pi. Just this one is very, very almost 0 degree. So this is very sharp angle. So this is the standard equation to calculate uy. To calculate uy, right? So any uy in this neighborhood. But here, okay? But here, I want to calculate this guy, okay? So for this guy, I need to use this as my crack tip. You understand? This is my crack tip. The distance between this point to my crack tip equals delta A minus x, because I establish x this way. So this is my R in this equation. That's the reason I have here. So this is R, this is R.
So you said that delta A is R down there?
Delta A minus x is R.
Oh, okay.
Right? This is my crack table, right? Delta A minus x is the R for my new crack. So that's the reason I have here. So for copper, we have two values. And for plane strain, we have this value. For plane stress, we have this value. Now this is uy because we want to calculate this one. We know uy, and then we need to calculate the sigma yy. And sigma yy is kia, right? And 2 pi x. For this original crack, I want to calculate the sigma yy at a point x. I can just use this equation. Theta equals 0, and theta equals 0 because it is just in the front of the crack. And theta equals 0. So sigma yy equals this one. I'll just plug in, okay? Plug in this equation. Now, so the delta U here will be equal to what? And delta U will be equal to from 0 to delta A, from here and to delta A, where delta A is so long. And it equals on 1/2 uy sigma y uy dx. You need to know multiply by 2. Right? Because when you want to close this is actual crack you need to you close this part and you need to close this part also. Do you guys agree? So that's the reason we have factor here, factor 2 here. So you can just plug in, and so finally you will get so this equation. So this very beautiful equation. So this is here, plug in here. So here, then you take the derivative, take the limit as delta A goes to 0, and you calculate the t here, right? So when we get here, guys, we need to do some manipulation. What is the manipulation? And we need to do some. We change the variable. Yes, we change the variable because for this integration, it is not easy to accomplish. Can I do it now? Give you 2 minutes. It's hard, right? But we can do some manipulation. Just let x equals delta sigma sin square theta, and then dx equals this, and we just plug in, and we can just convert this one to a sine function, the integrand. And finally, as delta A goes to 0, and we can have this part. So this is very beautiful. Because this is the very beautiful one. If we just use the concept of effective Young's modulus. So this G can be obtained using this equation: Ki square E prime divided by K2 square E prime and Kc square. Remember here is 2 mu. Okay? Because the mode 3 it is the outer plane shearing. It's outer plane shearing. So this is Young's modulus is not here, but it's a mu. The shear modulus is here. Questions? I want you guys. I hope you guys. I suggest that you derive this one. After you finish this derivation, and you will be an expert in the fractional mechanics. You have better understanding of this because we know the sigma and we know the displacement as a corrective. That's very good. And then we talk about the corrective plasticity. Okay. So actually, the linear elasticity is a very strict assumption, requirement, but most of the time we cannot do that. And then we have the corrective plasticity. For the corrective plasticity, usually we have this kind of plasticity. Plasticity, for this is a theoretical ideal plasticity. Ideal plasticity means that as long as the Young's modulus, this is the strain is greater than some value, and sigma y it yields. Okay? It yields, and the stress remains constant. So this is ideal plasticity. And for the commonly used one, and we have hardening, one. So this hardening means it goes this way, and then so it yields, and then go there, keep going. So this yield strength become higher and higher. Then if you just reload to unload this one, it goes down. So this line and this line will have the same slope. Okay, and here is called the plastic stream. That means that after this material yields, and then you remove the load. After you remove the load, the stream cannot go back to 0 instant, and you will have a plastic stream. So this is a plastic stream. So this is yield strength. So this is more common. So this is idealized the plasticity. And for here you can see, okay, so this is crack tape. So this is a crack front. And we have sigma yy. This is sigma yy. Okay, ideally for linear elasticity, sigma yy it goes to infinity as this r goes to 0. And however, it is not the case. We have this material yields. If the material yield, if yields, it we have here. So this is the yield strength. And so here, if you draw a straight line. So this straight line, this is the intersects with this curve, stress curve, and then you draw from this point, go down, and so this is Ry. Okay, so this Ry is the first order estimate of the yield of the plasticity area, plasticity, the size. And we have another one. For another one, I'm going to talk about this one later. So for here, Rp, I'm going to derive on how to get the Rp.